This is a video for AQA Mechanics, Center of Mass and Moments, section 1.4, where we're looking at the center of mass of a composite body. By a composite body then we mean something which has been made by adding together two or more shapes which are uniform objects, or removing sections cutting holes in them. Now because they're uniform, when we have a two-dimensional thing, we use a mass per unit area, which is normally referred to as K, kilograms per centimeter squared, for example, or it doesn't really matter on the units, it's just K per unit area. And then for the volume, if we have a three-dimensional shape, then it would be a mass per unit volume. If there are objects of different densities, then those masses may be different. For example, if one object is twice the mass per unit area, then we'd have to use K and 2K. Well, let's look at this example then, which is a letter F which has been cut out of card. We want to work out where the center of mass of the shape is. Well, one way to do this would be to divide this into three separate rectangles, and then to look at the relative masses of those, which would be proportional to their areas, and their centers of mass relative to some origin, which I'm going to take at this bottom left hand corner here. So the area of this part here is going to be 18, so it will have a mass of 18K. And the center of mass, obviously in the middle, would be at a position which is 1 and 4.5. For this piece here, it's a square, so it will have 4K, and its center of mass is going to be at a position which is 3, so 3 along from the origin, and then upwards it will be 3 plus 1, which is 4. So that's at 3, 4. And finally, the piece at the top here has got an area of 6, so it'll have a mass 6K, and its position is at 3.5 in the x direction, so 2 plus 1.5, so 3.5 here, and then a y value, if you count them up, 3, 5, 7, and 1, which is 8. Or you could do it from the other way of looking at that would be to say that it's 1 below the top of this part. So now we've got all the information we require to be able to calculate the center of mass of the composite body. I mean, the easiest way of doing this is to put this information into a table. So here it is in a table, and once we've got that, it is equivalent to having a system of 3 masses with known positions. So we can then calculate sigma mixi by first of all multiplying the mass by the x's, and then sigma mi and yi. And you can see that and check through that these are the values that you get. So that totals sigma mixi is 51K and the total mass 28. So x bar, as usual, is the sum of the moments in the x direction mixi divided by the total mass, and that comes to be 1.82. And similarly, y bar is the sum of the moments in the y direction divided by the total mass. So we get that the coordinates of the center of mass are at 1.82, 5.18. It's worth just thinking about where that is on our diagram. 1.82, 5.18 is round about this position here. And that makes sense from the diagram point of view. Don't be surprised if you find a center of mass which doesn't actually lie on the object itself. It is possible to have shapes where the center of mass is outside the object. In the second example, we've got a composite laminar which has been made by cutting holes in a card. So the card here is of length 45 by 30, which gives a total of 1,350. So taking K to be the mass per unit area, that would give us a mass for the rectangle before the holes are cut in it of 1,350 K. We're told that the triangle and circle have got areas 178.5 centimeters squared respectively. Now because these are holes, we can treat the masses as being negative. So we simply put in for the triangle negative 100K and negative 78.5K. Once you've done that, we need to put in the information about the centers of mass for each of the objects. Now, the center of mass for the rectangle originally is at its center of each side, so 22.5 and 15, and then we're given the centers of mass for the triangle and the circle. So this shows now the information on the table. Once we've done that, of course, we've now done this many times, we need to calculate MIXI and MIYI to then produce the totals, which are done here. You can check through those totals and make sure you're happy with them. And then to calculate the positions of the center of mass, X bar is going to be the sum of MIXI divided by sigma MI, and we can see from our table then that's 26627.5 K divided by 1171.5 K, and that turns out to be 22.7. And if I just jump forward now to the next slide, you'll see that Y bar worked out in exactly the same way, taking sigma MIYI on the top line, so that's sigma MIYI divided by the sum of the masses, gives a value of Y 15.3. Again, just worth checking roughly where that is. 22.7 is around about halfway along the one side, and 15.3. So it's very close to the center, which is again not surprising if you think about the positions of the holes that have been cut out. Turning now to three-dimensional objects, you'll be given in formula sheets or maybe in questions the positions of center of mass of certain objects. Here we're looking at the position of center of mass of a hemisphere, which you're told is 3/8 of the radius above the center of the base. And the center of mass for a cone is 1/4 the height, again above the center point of the base. So these are things that you can look up. You don't need to learn them. You don't need to prove where they come from either. So they can simply be quoted without proof. Here we're looking at a toy which is made up of a hemisphere and a cone, as we've just been discussing. To work in three dimensions, we need to take K to be equal to the mass per unit volume, and then therefore we need to work out the volumes of each of these objects. Now for a hemisphere, the volume is 1/2 the volume of a sphere, which is 4/3 pi r cubed, and substituting the value r equal to 3, then this turns out to be 18 pi. So the volume of the hemisphere is 18 pi. The volume of a cone, which is this downward one like this volume is 1/3 pi r squared h. So substituting r equal to 3 and h equal to 6, that also turns out to be 18 pi. So we can say that the masses of each of these are 18 pi k. The positions of the center of mass will be on the axis of symmetry, which comes down through here. The easiest point to take as our origin is this point here, because then we can use those formulae that we just looked at that you can quote, remember. So the position of the center of mass for the hemisphere is at 3/8 of the radius, so 3/8 multiplied by 3 is equal to 9/8 above that point. And the position for the cone is at 1/4 its height, so this one here will be at 1/4 multiplied by 6, which is 3/2. So now we've got all the information we need, and again we can look at that in a table form. You'll see here the fact that the cone center of mass is below O and the hemisphere is above means that we need to make one of them positive and one negative. So I've chosen here to make the hemisphere positive and the cone a negative distance. Once we've done that, usual procedure, calculate mi, yi and the total, and then y bar will be the sum of mi, yi divided by the total mass, so the sum of mi. And there you can see that we get a value for y bar of -3/16. So -3/16, just about 1/4 of a centimeter, so somewhere around about this position here for the center of mass of the composite body. In summary then, to calculate the center of mass of a composite body, we treat each part as a mass at its center of mass and relating that to the size of the object. So for 2 dimensions we'll use a mass per unit area, and in 3 dimensions a mass per unit volume. We can add together 2 parts, or we can even subtract a part or a piece cut out from a lamina or an object. And then if we've got a line of symmetry, we can use that and say that the position of the center of mass for the whole object will lie on that line of symmetry. Well, that concludes this video on composite bodies, and in the next one we'll be looking at the center of mass by integration.